Main Condition Assessment Part 1 webcast, Choosing the Right Technology, sponsored by InfoSense. Before we begin, I would like to quickly review a few logistics. All the PDF PowerPoint presentations are available for downloading at WEF's FTP link. This link was distributed via email yesterday and will be distributed again for tomorrow to anyone that registered after the time of distribution. The FTP link for this webcast also has information on how to receive professional development hours for those eligible to receive these training credits. There are 2.0 PDH credits for this webcast. You will need to complete the evaluation form to receive the PDH certificate. Your feedback on this webcast is important and helps identify future webcast topics that are timely and helpful to you. Please follow the PDH instructions and check with your state accreditation agency on how to receive this credit. During this webcast, while you cannot speak directly to the presenters, you will, however, have an opportunity to submit questions by typing in your specific questions via the pane that appears on your PC. Today's moderator, Mr. Reggie Rowe, will be accumulating questions and direct them to the presenters at the end of the webcast. We will be recording this webcast. A link will be sent to all registered users tomorrow so that you can share it with other colleagues who could not attend this webcast. If you have any additional questions after the webcast has ended, please email webcast with an S at wef.org. Before we get started, I have a poll question for everyone. Let me go ahead and launch that. The question is, how many people are participating in the webcast today at your computer? If you're participating by yourself, please respond 1. If you're participating in a conference room, for example, just do a quick head count. All right, I'll give a couple more seconds for everyone to respond. It looks like we have about 80% right now, so if you could respond, that would be great. Okay, thank you so much. I'll go ahead and share those results with you. Looks like we have about 82% participating by themselves today, so thank you for responding. I'd like to thank Mr. Rowe for moderating today's webcast. Mr. Reggie Rowe is a Senior Principal Condition Assessment and Rehabilitation Services Technologist with CH2M Hill. Reggie?
Thank you, Rebecca. Today's webcast is brought to you by the WEF Collection System Committee and its webcast subcommittee. The committee is made up of the chair, Keith McCormick, vice chair, Rudy Fernandez, and the WEF staff liaison, Christine Radke. The subcommittee members are Abraham Araya, Christopher Curl, Maddie Ingalls, Chris Gainham, Scott Helfrich, Chris Johnson, John Nelson, myself, Chip Smith, and Diane Samego. And then we have the WEF, Rebecca, who you have just met, our webcast program manager, and Christine as our WEF liaison. I think it's important that we note that the pressure pipe and force main series supports an EPA research program recommendations that came from an EPA initiative, Task Order 59, called Condition Assessment of Collection Systems. That started from an initiative the EPA had in 2007. It was called Innovation and Research for Water Infrastructure for the 21st Century. One of the first products was a May 2009 white paper on condition assessment of collection systems, and it included a technology forum results that the technology forum was held in September 2008. It was an assembly of experts across the country. Rob Valet, our past Collection System Committee chairman, was on that. And from that, it listed a number of critical technology gaps, of which this pressure and force main inspection was one of those critical gaps. It's important that our webcast subcommittee thought it appropriate to feature this recommendation in this series series of webcasts, and that's why you're seeing that today. Related to that task order 59 are a couple other very informative resource documents. Let me mention those real quickly. In April 2010, there was an innovative and internal camera inspection and data management for effective condition assessment of collection systems. And then August 2010, report on condition assessment of wastewater collection systems. These are easily located on the Office of Water site of EPA's website. Today's speakers, we have Dr. Rob McKim of Louisiana Tech, Mr. Kelly Durr of Brown and Caldwell, and Mr. Mark Lambert of King County Wastewater Treatment Division in Spokane, Washington. The Webcast Committee asked each speaker to emphasize special areas or activities for this presentation series. It is one of 3 that you've seen advertised through the WEF communications. And for today, Dr. McKim was asked to talk more on the how you get started with walk through the array of different technologies and screen them for particular local criteria. Mr. Durr was asked to discuss the approaches for analyzing the data results and how do you handle the data. And Mr. Lampert was asked to talk about how do you integrate all these processes to site-specific applications and case studies. We also asked each presenter if they could add a little case study with their presentation to do that as well. So let's go to the first speaker, Dr. Rob McKim. Dr. McKim is he's the director of the Trenchless Technology Center and program chair for the Construction Engineering Technology Program, and he's a global technologist for CH2M Hill. Dr. McKim has over 35 years of civil engineering experience in conventional and trenchless technology projects, and evenly divided as a researcher and a practitioner. He is a registered professional engineer specializing in the research and practice of trenchless assessment, predictive modeling, asset management, rehabilitation, and installation of pipeline and tunnel infrastructure systems. I want to welcome Dr. McKim.
Well, thank you very much, Reggie. I'm hoping everybody can see my screen. I want to thank Rebecca for holding our hands, for getting this technological marvel going here, and I also like to thank InfoSense for sponsoring it, as well as WRF for inviting me to participate. I'd like to talk for a second or two about the Trenchless Technology Center. We are a center that was founded in 1989. We are an integral unit with the College of Engineering and Science at Louisiana Tech University. For the past 25 years, we have been working a lot in the research and the education of trenchless technology. In the early 90s, we specialized mostly in things like microtunnel, directional drilling, and pipe bursting, and then industry was moving on more towards rehabilitation from the mid-90s to the mid-2000s, and now we're finding that there's a lot of interest in the assessment and inspection. So we're rechanging our focus into the inspection and assessment areas, as well as keeping up with other technologies. I'm getting pop-ups on my screen here. I'm not sure how to end that. We have about 14,000 square feet of laboratory here in Louisiana Tech. We work a lot with municipalities. We have about 10 to 15 municipal forums a year where we reach out to utilities and end users and try and connect the technology to the people who are going to be using them. I would like to point out that most people, when they think of Louisiana, They think of New Orleans and sort of everything on the southern part, but we are in the northern part of Louisiana, so we don't get to experience the fun things like Mardi Gras. So just to let you know, we are up sort of not in the fun part of the world. We work very closely with an industry advisory board. We try and make sure that our research is relevant and focused onto what's happening today. And the Industry Advisory Board includes a number of utilities, some of the major utilities such as Atlanta, Boston, New York, Los Angeles, Seattle. We also have a good contingent of consultants, contractors, and suppliers that are part of our about 40 members. So we are tied very closely into industry, and we do listen to what our Industry Advisory Board asks us to do, and that's why we tend to change focus. We've noticed sort of mostly since about 2005, the number of pressure pipe inspection technologies really has exploded. All the way from over here, we can see basically an optical scanner, which is sort of the next generation of the CCTV. We've seen laser scanners, which are the next generation of laser profiling. We've also moved into the electronic age, where we're starting to use remote field eddy currents to find out what's happening in the pre-stressing wires of pre-stressed cylinder pipes. This one right here that we're seeing is delivered through a robotic platform. We also are able to use this through a free-swimming pipe diver platform. And this tells us a lot about what's happening on the wires. Have they corroded, and are they doing their job for pre-stressed cylinders? We've also moved into a lot of, I guess, non-destructive or non-service disrupting technologies, such as guided wave technology, which basically sits on the outside of the pipe and uses acoustics to tell us what's happening to the stiffness and to the pipe wall. At the Trenchless Technology Center, we're working now with some industry partners to develop ultra-wideband technologies so that we can combine it on a robotic platform and find out what's happening in the pipe wall, and identify voids behind the pipe wall. And of course, there's what I consider eyeball mark 1, which we can't ignore. It's actually putting boots in the pipe and having a look at it. So we're finding that there's a lot of new technologies coming out that are not necessarily well understood. So there was an effort in the about 2010, 2011 from an Industry Advisory Board to start to try and categorize and start to work with industry to bring the technologies forward so that people understand it. I'm not to say we're the only organization. A lot of very good organizations, including WRF and EPA, have worked on this. We just tried to do it slightly differently. So we did a joint effort with our Industry Advisory Board people. We found that there was an emphasis on pressure side, and both the IAB and ourselves are seeing more need for pressure side. We're always hearing from the wish list that we get from our Industrial Advisory Board, what do you want to do? And most of them are saying we want to know more about pressure pipes. So we did an inventory of the technologies we could find, and we found in 2011 39 technologies under 17 technical categories. We'll talk about the categories later. So in order to control this actually vast amount of data, we put together a matrix, which I will show. And this is only part of the matrix, and to walk you through it, on the left-hand side we have listed the technologies that we found, and then sort of along the x-axis, I guess, we start to define what the technologies can do. Are they pressure pipes? What type of materials will it work with? What's the information that they're gathering? What is the data that they're gathering? And this was a way that we attempted to try and organize the data, because there was it was very, very difficult to get your head around what all the different technologies could do. And this actual matrix is available on the website, either through our Trenchless Technology website, or you can go right to the HTTP site.
Hey, Rob?
Yes?
That pop-up that keeps coming up, if you just click the first option, that'll stop bothering you.
Oh, thank you very much. I was wondering if everybody was seeing that. I thought I had those turned off. So
That's okay.
next time it comes up, I will do that. Some of the matrix input variables that we were looking at that we found were necessary for making a reasonable decision about which technologies you should use, and to say change color scheme. Which one should I hit, Rebecca?
Just click the top one, yep.
Right there? Okay. Hopefully. Now what's happening here? Okay, so sorry about that. Rebecca, thank you for talking me through that. Some of the things that we need to know about each technology, for example, is it useful for gravity or for pressure pipe systems? What are the pipe flow conditions it can work on? Does the pipe need to be empty? Can it work under full flow conditions, partial flow conditions? What is the pipe material that the technology will work with? Is it metallic? Is it plastic? Is it reinforced concrete? Is it a very complex pipe wall system, such as pre-stressed cylinder pipe? The variable detected, are we looking for leaks? Are we looking for cracks? Thinning of a wall? Are we looking for corrosion in wires? The degree of technology maturity, in other words, what's the probability that when you purchase that technology or utilize that technology, it will give you the information as advertised? And that means, do you have the contractors who can actually execute the work, and do you have people who can interpret the data? Feature location accuracy, for example, some leak detection systems will tell you, well, we know you have a leak from this point to this point. We can't tell you exactly where it is. Other leak detection technologies can tell you exactly where the leak is. And sometimes you need to know exactly where the leak is, and sometimes you just need to know that there's a leak in your system. Feature capacity and severity. Do we want to know how thin the wall is? Do we need to know what the rate of leakage in gallon per minute is? So does it just tell you, do you have a leak, or will it tell you the volume of the leak? What are we measuring? Are we looking at the joints, the barrel, the wires of the pipe? So what part of the pipe are we actually looking at? Because some technologies focus on different parts of the pipe. Data processing, we're finding now that we're getting more into things like GPS. The signal that comes back is multiple signals, and they're really not usable or user-friendly until you do a fair amount of data processing on it. So a lot of our technologies now collect the data, and then there's several days of data processing before they're put into a format that you can use. And data interpretation, we're finding that quite often once we get the data in a sensible format, what does it actually mean? Other things like size of pipes, technologies that work in 4-inch pipes may not necessarily work in 72-inch pipes, and also the cost range. So in 2011, we found that we had these technologies. Here's the inventory of it, and I'm sure we're all fairly familiar with it. Some of these, CCTV, just visual walkovers. Some of them you may not be familiar with, such as X-ray tomography, infrared thermal, and you'll notice that there are some technologies such as InfoSense, which are not in here because this field is developing actually extremely rapidly. And so we're contemplating redoing the inventory for 2014 and updating the new series of technologies that are out there. So we have a lot of technologies, and the question is, which technology should we be using and when? With the help of our Industrial Advisory Board, we'd say, how should we start organizing these? And the first thing was cost, because that's very high on the list of everybody. That's pretty well the first question that they ask is, how much is it going to cost? So we grouped them into what we saw were natural sort of lumps of material, groupings of material, so that be under $5 a foot, under $15 a foot, and greater than $15 a foot. And you can see things like potholing and guided wave, surface GPR, those types of things can be actually relatively inexpensive. Then we move into the CCTV and sonar, which is slightly more expensive. And then we get up into the high-end fairly expensive ones, which can exceed sometimes upwards of $100 a foot. What we found is there is a definite correlation between what you pay for and the amount of information and the quality and the accuracy of the information. Pretty much like anything, if you really want to know what's going on, you can spend a lot and you can get a full understanding or a very good understanding of the pipe, or you can spend a little and get a little bit of understanding of what's happening in your pipe. And what you want to do is make sure that you hit the sweet spot and just get the right amount of data for the minimum amount of cost. We also found out that the information we need to assess your pipe, for example, in the pictures here, we're seeing reinforced concrete and clay pipe. 90% of the information you need can be obtained by pulling the camera down, taking a look at what's happening on the inside surface, and then utilizing some kind of uniform system such as the PACP system to say what's happening to your pipe and what condition is your pipe in. These systems don't generally work terribly well whenever you have a complex pipe such as a pre-stressed cylinder pipe, because just looking at what's happening on the inside concrete core doesn't necessarily tell you what's happening at the other structural elements such as the barrel or the concrete outside the core or the pre-stressed cylinder, pre-stressed wires. Getting back to our matrix, we realize that it's really not a good selection tool. It's a good place to put your information, and it's a really good educational tool. Whenever you're trying to explain why you accepted or utilized a certain type of technology, it's very nice to sit down with the end user and say, I used technology X because this is the material, this is the service conditions you have, this is what you really need to know. So we found that it was more of an educational or explanation tool than where we originally thought we were going, which would be possibly an automated matrix that would pop out an answer as to what technology you should be using. I want to point out we are certainly not the only people. The Trenchless Technology are not the first or the only people doing it. A lot of really good organizations such as WRF and EPA are also working on this. We're just taking a slightly different approach to it. Previous work has been done for the first little while. For example, back in the late 2000s, we were just trying to figure out which technology would be used for gravity and pressure. Then we started asking a few other questions. What type of material do the technologies work with? How effective is it? Service applications. So we think that our matrix is sort of the next evolution of these tables that you've seen that were generated by other organizations. How do we organize these technologies in a usable tool? Well, understand the expectations. What we have found is many utility owners are using CCTV of a gravity system as a benchmark, and that's about $5 a foot. That's probably not a realistic expectation on the pressure side. The pressure technologies can go from under $3 a foot to over $100 a foot. Generally, pressure pipe is more complex as well. We're still learning, so you get what you pay for. I'd like to end up with a very nice little example case study. This is in New England, where there was a utility with 500 meters of 600 millimeter pre-stressed cylinder pipe on a water intake, going from a water intake system underneath the interstate and along an interstate right-of-way, which was made it a very critical line into a water treatment plant. We had some fairly, and it was all pre-stressed cylinder pipe, some fairly hefty site restrictions. We could only have the system out of service for a 6-hour window, and that was, there's no question, that's all we had. Very limited access points at the pump house and the plant, and we also had gate valves and venturi meters that we had to get through. We were able to go in what I consider the low-hanging fruit, get a lot of information from maintenance history operations, obvious issues. Then we started to say, what technologies can we use? In other words, let's look at the low-hanging fruit, get the cheap technologies first, and then work towards some more expensive technologies when we know more about the system. So we started out with our grouping based on cost, and we sat down with the utility owners, and we said which of these technologies will work given our specific situation. You can see that visual, potholing, straight current, guided wave pipe stiffness, acoustic leak detection, they work. Group 2, we had Sahara and Smart Ball, and Group 3, remote field eddy current transformal coupling. So we had a group of technologies that would actually work and give us decent information. Which one should we use? We selected the guided wave to do the entire line because that was a very inexpensive technology, sort of at the $5 a foot range. And then we used that to focus in the remote field eddy current for the high-risk sections. The guided wave, basically, you need access to the pipe at 2 locations, 2 or more locations, and it will tell you information about the pipe between those locations. You can't get any more specific as to where the problem is, but it will tell you the weakest part of the pipe between those 2 sensors. The remote field eddy current, it measures the actual wire breaks, and it's a little bit more of an expensive technology, but we want to use it where we should be using it. What we found is that using the very inexpensive technology as a screening tool, we used the guided wave for the entire section of pipe from the intake all the way to the sewage treatment plant, and we found that there were no major problems or no real problems in the first 3 sections. But once we got inside the limits of the treatment plant, that's where we had a lot of problems. So we were able to identify from guided wave that we really should be focusing on about the 150-foot section just outside the plant. And so that's when we brought in the remote field eddy current. The pipe diver was a free swimming system, and we used the approximately $50 a meter, $50 a foot plus technology only on that small section. Conclusion, one size fits all inspection technology probably will not work, give you the information that you want. For pressure side, you really need to understand the limitations and what each technology gives you. The matrix will help you with that. It certainly doesn't solve all your issues, but it's a good place to get information. Using low-cost inspection technologies as a screening tool can be very cost-effective whenever you combine it with some of the other technologies. So that's my presentation, and I will hand it over to the next speaker.
Thank you, Dr. McKim. Now we'd like to bring on Mr. Durr. Mr. Durr has over 40 years of experience in the planning, design, and construction of water and wastewater facilities, including over 16 years overseas, chiefly in the Middle East and Northern Africa. Since 1990, he has been increasingly focused on trenchless technologies, beginning with the rehabilitation and expansion of entire bridge systems for the municipality of Dubai and the United Arab Emirates. For the last 7 years, Mr. Durr has focused on the inspection and condition assessment of water and wastewater pressure mains. He has written over 60 technical papers, is on the board of directors for the Southeast Society of Trenchless Technologies, and currently serves as a senior associate with Brown and Caldwell based in Raleigh, North Carolina, and is the firm's technical leader for trenchless technologies in Mid-Atlantic region and co-leader of the firm's condition assessment and rehabilitation community of practice. Mr. Durr.
Reggie, thank you very much. I appreciate the opportunity to address the folks in this webinar. I think it's a great forum. As you may have gathered, we're sort of taking this in proper sequence. Dr. McKim talked about the various technologies out there. I'm going to talk about what we use, what we do with the data that we get from these pressure main inspections. And to do that, I'm going to use a case study that looks at one specific tool and how we use that tool to develop our approach to then using the data to select follow-on actions, the 4 R's as I'm calling them. I'll get into that in a minute. You can do inspections of pressure mains are all our buried infrastructure for a number of reasons. One, we got into it because some of our clients had consent decrees that they had to get into it. In this case, this coastal community in South Carolina had a lot of concerns about the condition of their wastewater force mains. It had not been in there to inspect them. They had some failures, as you can see here, and they wanted us to do a complete inspection of their inventory. As Rob said, as Dr. McKim said, you can really get what you pay for. And in this case, they really wanted a very detailed inspection of their force mains to assess the risks that are in there. We did a criticality analysis, risk-based, and we identified this one force main as being a very high risk, had previous failures, and went through very critical residential and commercial areas that they did not want to have spilling. It went from a pump station on the sound side of this barrier island, went inland up to a high point, and then ducked down and discharged at a wastewater treatment plant on the ocean side. The failures, as you see here, occurred in the crown of the pipe in the down gradient portion of the section where the hydraulic grade line dipped below the crown, and you get a lot of internal corrosion at that point. At this point, they still had about 4,500 feet of pipe that they felt was still, hopefully, was still in good condition, and wanted us to inspect it and determine its condition and what to do with it if they had problems. Because they wanted a very detailed data, we decided to use the remote field eddy current tool. It's called the Sea Snake, provided by PICA Corporation, which is a subsidiary of Russell NDE. This picture shows the tool just as it's coming out of the 16-inch diameter ductile iron pipe on the first run. This tool can either be free swimming or winched. Because we already had holes in the pipe for failures, it was easier to winch it through. This is a large table. This is actually one small part of the data that we got from the Sea Snake for this line. And I wanted to show this table for a couple of reasons. One, each row is a distinct, discrete pipe, stick of pipe. In other words, the first 4 columns indicate the number of the pipe and where the pipe is located. It actually identifies each joint of pipe. The next 4 give you average wall thickness as a percent of a calibrated nominal wall. And what's really a value to me, to us, these 9 columns give you the data on the top 3 defects in each pipe stick. The location along the axis, it gives you the clock location, and it gives you the percent remaining wall thickness. Very good data. What the client was excited about was that this showed that the first 650 feet of the force main had significant wall loss. A lot of sticks with multiple deep pits, and 8 actually had holes in them, probably filled with graphitic plugs. So they weren't leaking, but they still had the hole throughs already. What's interesting is that most of these defects were in the invert, whereas the pipe earlier had failed in the crown. Of more importance to the client, the remaining 3,900 feet of the force main, as it got away from the marine area, was in excellent condition. So if this data could be believed, they felt very confident they could avoid replacing that 3,900 feet of pipe, saving about a little over $500,000. And if so, then the cost of the inspection would have a 6-fold return on investment for them. They were very excited about this, but they wanted to verify it. So we went to stick number 3, which had a hole in it in the invert, and a pit with 13% wall remaining about 3 feet away from that hole. And we dug it up, pulled it out, and here's what we found. Exactly where the tool said it was, there was a hole in the invert, and 3 feet away was a deep pit. So with this level of confidence in the data, the client went ahead and replaced the first 650 feet of damaged pipe with a PVC C900 and is keeping the other 3,900 feet in service. Not only that, but right now we're conducting a pigging operation on the remainder of his ductile iron force main inventory. We're pigging one of the longer lines today. I hope to put the sea snake in it probably tomorrow. The question was, obviously, if you have a hole in it, that's easy to decide what to do with it. And it was easy to make the decision to replace that very badly damaged 650 feet. The question now becomes, what if you're in between? If you have moderate wall loss, what do you do? How do you decide what to do? The first step in doing this is we converted all the percent wall thicknesses into actual inches using the nominal wall thickness that we got from the calibration test. This allowed us to convert all those percent wall remaining into inches of wall remaining. And then it was fairly easy then to back calculate the actual factors of safety that each stick of pipe was affording, because we knew the operating pressures, we knew that we gave an allowance of surge, we knew the wall, the pipe depth, we knew the surface conditions, live and dead loads. We're able to actually calculate the minimum factors of safety against both internal pressure and against external load. With this client, we came up with this category. If the factor of safety that we calculated under actual conditions was greater than 2, which is a standard design factor of safety, then the pipe segment was in good condition, and we only needed to re-inspect, perhaps on a routine inspection cycle. If it was less than 2, but greater than 1.2, we determined the pipe was deteriorating, but still serviceable, depending upon where in that range it fell. And we can either re-inspect at an accelerated rate, say in 5 years, or if it's very close to 1.2, or if it's got a lot of holes in it, then or pits in it, then we may decide to repair or rehabilitate it now. And again, if the factor of safety was less than 1.2, then it's heavily deteriorated, and we needed to do something, depending on how many defects there were, either repair it, rehab it, or replace it. We used the 1.2 as a threshold to give our client a little bit of a breathing space, so if he wanted to get the pipe segment onto his CIP, he had some time to do that. So this is a very initial step in deciding what it is we need to do. However, we still don't know what kind of repair we want to use, what kind of rehabilitation program, or when we're going to do it. So the next step was to develop a type of a selection tool, and for that we are developing some very preliminary ideas of defect codes for pressure mains, starting with actionable defects and then progressing to observations and screening, things that we can use to actually make decisions on what to do for each of these each of the defects. Obviously, we started with the PACP codes. We had about 5 that made the transition that were applicable to pressure mains. There are some more out there, but these are the 5 basic ones. Cracks, deformations, leaks, lining failures, these are all fairly common to both gravity and pressure pipes. And for these, we use the same codes, same modifiers as PACP, and same severity grades from Appendix D in your PACP manual. To those, we've added defect codes that are more based on the failure modes of pressure mains. Wall loss is a failure mode in gravity lines, but it's not nearly rigorous enough for us to really determine what the condition of a pressure main is. So here we've expanded the wall loss category and made it much more rigorous based on actual percent of wall loss and wall remaining. So and also wall pitting, tuberculation, particularly for water mains, and for pre-stressed concrete cylinder pipe, we're adding wire break zones, wire break rates, and we can even look at cylinder defects. Some additional codes, exterior staining, particularly for pre-CCP or RCP. If you've got some rust stains in the exterior of the pipe, that gives you a good idea. You need to look there and see what's going on. Plastic pipe, really the only defect, the only observation we can make is do you have soil voids externally to the pipe. We also included screening codes. These are not condition assessment codes or defects. They're not defects. They're actually indications of where you may have a problem. Acoustic systems that Dr. McKim was talking about can tell you where you have leaks or gas pockets. And that would be an indicator of possible internal corrosion. Doesn't prove that there is corrosion, but it says that's a good place to look. For external corrosion, we have a number of external tests, corrosive soils for straight currents, for active cells. There are more tests out there, but these are the ones we're putting in, and I invented a couple of codes and modifiers for those. The system elements, one of the key challenges we've had in inspecting pressure mains is the lack of a complete data sets in utilities GIS systems. It is surprising how many clients don't even know where their force mains go. So we found it very important to go in and improve their database on valves and valve types, fittings, locations, fitting types, house connections. This is not only important for your database, it's also important for planning your inspection program, since many tools, such as the inline tools, cannot go through a plug valve, for instance. Or vendors don't like to put them through plug valves. The little lip catches other elements that are good planning elements to know when you're putting together an inspection program are diameters of the pipe, material changes, has there been a port repair. For inspecting water mains, we have found that sediment in the bottom of the pipe can be a little bit of a problem, particularly for some of the inspection tools, which may rile up that sediment and cause turbidity issues. So you need to know about that before you, or address that before you go in with the inspection. Now, the whole purpose of this, while we're developing the factors of safety and the defect codes, is to help us selecting the next actions, which I've called the 4 R's: reinspection, repair, rehab, and replacement. And we started, as I said, we started with the PACP approach, which has a grading system 1 to 5. And we've added more codes for the defect, more defect codes for the failure modes. And it's different for each type of pipe. We've developed a very simple tool. This is really at the very beginning of our development of this decision tool. This was actually developed as a training instrument device for our in-house engineers, and we've had clients ask us for this as well. This is simply the first page in about, I'd say about 10 pages of code. It's meant to be used from left to right, and I'll break this down so you can see it a little better. I'll show the left half first. This is the defect codes that you found in the pipe. This is for ferrous pipe. And the first defect type was loss of wall thickness. And I'll just run through it from left to right. It's a moderate loss of wall at numerous sites in this pipeline. It's a fairly older pipe, and it's in a sensitive area, so you can't trench. These are all just as an example. And for this combination of criteria, I'm giving this a grade of 4. Using that, we then move to the right-hand side of the table, which gives us the potential options for addressing whatever defect we found on that pipe stick. The X's mark the approaches that are acceptable to the client and are feasible for this kind of defect and this kind of material. You'll note that there are a lot of other technologies out there that are not in this table. These are just the ones that this client likes to use and prefers to use. These are customized for each client. The yellow is my indication, in my opinion, of what would be the optimal approach for this particular combination of modifiers. I'm saying this is a cured-in-place pipeline rehabilitation. Very simplistic, very early days in this, and I would love to get input from people on the additional codes and additional ways of using this simple approach. Just to summarize, we have described an approach for using the factors of safety based on the data from our inspections to prioritize the pressure mains for follow-on work. And to do that, we've developed a set of defect codes, very early days, and a method for using defect codes to develop a quantifiable condition assessment. Again, as I mentioned, this was first developed as a teaching tool for our engineers getting into this approach, but a lot of our clients have asked us to help them develop a similar tool for their own engineers. And that is the recap, and I'll turn it back over to Mr. Rowe.
Thank you, Mr. Durr. Now I'd like to introduce Mr. Mark Lambert. Mr. Lambert has served as a senior wastewater engineer in Seattle for the King County Wastewater Treatment Division. He is a project manager for the force main pressure sewer and siphon assessment and inspection project that was completed in 2011. And part of that project, planning project for the review and update of the system-wide pressure pipeline inventory and review of the system's failures and inspection status and options for further inspection. Mr. Lambert was the lead engineer on acoustic inspection for the North Beach force main, and as part of his team, he was tasked with the overall assessment of the North Beach pump station and force main system. Mr. Lambert has also had 15 years of conveyance planning and modeling with the agency, and he provided comprehensive and project-level engineering support for capital facility planning. He's also served 10 years as the surface water engineer for the King County Water and Land Resource Division, where he did planning, design, and construction engineering for flood mitigation and resource protection projects. I'd like to welcome Mr. Lambert.
Thank you, Mr. Rowe. I was asked to go over some actual projects that we've done here at King County to kind of go over how we went about choosing the technology, what we did with the technology once we, what we did with the information we found, and how we use that information to go along and make decisions. The two case studies I'm going to look at were a sonar inspection of the Ballard siphon and an acoustic force main inspection on the North Beach force main. Start off with the Ballard siphon. The Ballard siphon's 1,300-foot long wood stave dual inverted siphon going under the Ship Canal in the Ballard neighborhood in North Seattle. It was constructed in 1935. It has twin 36-inch diameter barrels, and they're actually banded together during the construction. You can see in the portion of the plans here, they're tied together. That gave us a little bit of concern that if we did something or influenced one pipe, it would probably influence the other one also. Just as far as the location goes, it's in an industrial area. It's very tight conditions as far as being able to provide work areas to access it. We really didn't have a whole lot of options as far as being able to access other than the forebay and the afterbay. The Ballard siphon was one of a group of initial sonar siphon inspections for WTD. Back in the mid-2000s, we were investigating numerous technologies to inspect all of our siphons that we really hadn't looked at previously. And the Ballard siphon was one of a half a dozen or so that we started with in 2005. A number of the siphons now are on a regular sonar inspection with some newer technology sonar, that later generation that is able to tell us some information that we weren't able to get on the first one here. Once again, it was initially inspected in 2005, in late 2005, and again in early 2007. Just prior to the second inspection in 2007, we pulled the pig through the through both of the barrels, and noticed on the 2007 inspection that some of the results differed. Some of the cross sections that we were seeing in the sonar profiles were different. Just as an example of some of the graphics that we got initially in the 2005 inspection, you can see it appears there's a collapsing of the crown of the pipe at about the 90-foot mark, and the image on the right is some of the raw data that you see during the inspection. Image on the left is some post-process data based on a conglomeration of some of the data that was collected. Once again, the second inspection did show some changes in the in the cross sections. In this case, at 95 feet, the image on the left, we actually showed more obstruction in 2007 than we had in 2005. Once again, this was after the pigging. And then at 900 feet, the image on the right shows that we actually had less obstruction in 2007 than we did in 2005. Now, this caused a number of us to wonder what exactly was going on, and project team members kind of huddled together, and a decision was made to do a partial video inspection. And there was some concern at that point of pumping down. The sewage was much too murky. We couldn't see, the inspection teams couldn't see anything in the pipe. So there was a decision made to do a partial pump down. Some calculations were made using some basic fluid statics of how far we could go before we were really concerned about either floating the pipes that were buried in a bunch of sediment or causing the pipes to collapse from external pressure. So what was decided is there would be a monitored pump down where it would run a submersible down from the outlet and begin pumping in the isolated siphon. We were able to divert to one of the other siphons. And then the camera simply followed the water surface down from the inlet. And lo and behold, we got about 70 feet down and revealed that the deformity was fat, oil, and grease accumulation in the crown of the pipe, which was something that we had found in a number of the other inspections subsequent to that, is that the crown of the pipe tends to collect fats, oils, and greases. And along with this, we also found a number of minor leaks. As far as the overall results for the project, this was part of an assessment that was being done on both of we have another major siphon just to the east of the Ballard siphon, the Fremont siphon. Those two siphons are the only connection conveyance points from North Seattle to South Seattle across the ship canal. So this was part of an overall assessment of what we were going to do in the future. Both of the siphons are very old. The Fremont siphon is actually older than this one. And while the inspections were going on, there was a great amount of work being done to look and see what it would take if one of them failed, how long it would take us to actually construct a temporary system. And based on the results of that analysis, along with the information that we gained from the inspection, an overall risk analysis resulted in replacement of the current siphon. That project is just wrapping up as we speak now. They're pulling HDPE through the old wood stave barrels. We tunneled and installed a brand new high flow siphon. So that replacement and rehabilitation is giving us a lot greater capacity through the Ballard siphon, more redundancy, and some more flexibility on how we manage our flows from the north end of the system down to the West Point treatment plant. This project, the North Beach force main acoustic inspection, was one that I had a lot more involvement in than I did at the Ballard siphon. North Beach force main is a 14-inch diameter cast iron pipe laid in the tide zone in the beach in 1961. About 5,000 feet of it runs in the beach parallel to some railroad tracks, and then it turns to the east and runs about 2,000 feet in a park up to the Carkeek stormwater treatment plant, stormwater pump station and treatment plant. The assessment was part of an overall force main pump station assessment. There were some capacity issues. There was the thought that we might have some blockage in the system, and we were also interested in determining what we thought the remaining useful life of the facility is. Unfortunately, it's a single force main, so our access and isolation or ability to isolate for inspection was very limited. So that shaped a lot upon what we were able to actually use for inspections. There's a quick diagram just showing some of the constraints where we are running along the North Beach area and then turning east and heading up to the Carkeek pump station stormwater treatment plant. As I said, we had limited access. Number of the technologies would have required pigging. We talked to some of the pigging contractors and some of our folks that have done a fair amount of pigging. There are some 90-degree bends identified in the record drawings. We are going to have to do some fairly significant construction at the pump station to be able to actually launch a pig. And so we were really limited by what we could deliver, what sort of device we would be able to deliver for the inspection. So we went through a screening process similar to the processes that were described by the previous presenters. Out of that, Smart Ball was selected. It's a free-swimming technology, basically a foam ball with an acoustic device in it, developed by Pure Technologies. We sent the basic information to the vendor. They reviewed and confirmed the feasibility. Actually came out and did a walkthrough. As part of the project, it was identified that we needed steady pump station flow to maintain a constant velocity, well beyond what average flow was going to be at that pump station. So at that point, we had to go and talk to our partners at Seattle Public Utilities, the major water purveyor in the Puget Sound or in the Seattle area. And they have a fairly standard, if you have a construction project, they have a fairly standard process that you go to get a hydrant. And hook up to a hydrant, and they stick a meter on it, and they charge you for any water that you're using. And that all seemed pretty well until I told them that we needed about 1,000 GPM for about 2.5 hours. And we ended up finding a hydrant that happened to be a fairly high-pressure hydrant also, so about 160 PSI. And with the help of a on-call contractor and our construction crews, and once again our colleagues at SPU, we were able to successfully deliver for a fairly long time. We ended up running it for about 3 hours of hydrant flow to be able to get the pump station up to a flow rate that would deliver the Smart Ball from one end to the other. So again, we were able to, retrieval was fairly easy because we have a trash rack at the pump station, so when it exited the force main discharge structure into the pump station, it simply was retrieved on the trash rack. On the upstream end, we were able to launch the device through a valve that normally has an air relief valve on it. So we were able to simply close the blind flange, hook the launch device onto the blind flange, and they were able to launch the device very easily. As far as the inspection results of the North Beach force main inspection, there were no identified leaks. They did identify trapped gas locations along the alignment, and those trapped gas locations were used for some subsequent coupon testing. This is fairly standard type of test, aside from the fact that it's in the beach. The coupon testing involved quite a bit of permitting from our permitting staff, who did an excellent job, and then delivered heavy equipment via barge onto the beach. We ended up taking 3 coupon samples along the alignment using standard hot tapping techniques. Those coupons we were able to compare to some previous coupon testing that had been performed in 1989 and gave us a bit of a benchmark, and we were able to determine that the force main does in fact have a 20 to 30 year service life remaining in it based on the coupon testing inspections. We're also hoping that as some of the technologies are advanced and the delivery devices are advanced, we will continue to be able to test this again and get an idea of exactly what we can look forward to as far as being able to maintain and not having to parallel or come up with an alternative for this system. Some of the additional benefits of the smart ball test is just the fact that we were able to deliver the technology. There was a number of thoughts with some of the folks in the agency if we'd be able to actually do that. We were able to confirm that. And we were also able to use the hydrant test to do some sustained peak pumping capacity tests at the pump station. Normally, if we wanted to do that, we would have to wait for it to rain hard and come into a CSO event when most of the operators are fairly busy with other issues at that time. We were able to, in a rather controlled state, use that hydrant flow to test the peak pumping capacity and establish some current pump curves. So that is pretty much it for the examples that I had.
Okay, thank you. Thank you, Mr. Lambert. Let me encourage you to enter your questions. We have plenty of room for those. But before we take on the question and answer portion of the webcast, we want to go to our sponsor now. And I'd like to introduce Mr. Alex Churchill, representing InfoSense. Mr. Churchill.
Thank you, Mr. Rowe, Ms. Arvin, and our presenters for providing an excellent educational program today. We at InfoSense are honored to have had the opportunity to sponsor today's event on behalf of our product, the Sewer Line Rapid Assessment Tool, or SLRAT. I'd like to take a few minutes now to focus away from pressurized systems, water systems, and force mains that we've been talking about here recently, and talk with you about a new tool for your collection system toolbox that can help reduce overflows and prioritize cleaning efforts in gravity-fed systems. The product, the Sewer Line Rapid Assessment Tool, or SLRAT's objective, is to help wastewater collection system operators obtain condition assessment information, and specifically blockage condition information about their smaller diameter lines, say specifically focusing on those in the 6 to 12-inch diameter range. which on average we've found comprise approximately 90% of pipes in the U.S. and also are where approximately 90% of SSOs tend to occur. The SO-RAT is designed to provide this blockage condition information in a practical, simple package that provides the assessment in real time and quickly. Two operators can inspect 10 to 25,000 feet per day and at low cost, feet per foot. At this point, I'll mention much more information is available on our website, as shown on the previous slide at www.infosensinc.com. And I'll also mention that I'm available to answer any questions afterward at the email address and phone number, again, presented on the previous slide. So let's take a quick look at the technology itself at this point. I'll first give you a little background. InfoSense is a Charlotte, North Carolina-based manufacturer of acoustic inspection technologies that was formed in 2007 by university professor Dr. Ivan Hallett to commercialize the technology he developed in partnership with and at the behest of the local wastewater utility there. With what Dr. Hallett learned from Charmac in the early stages of their work together was that utilities had tools to inspect pipes, such as CCTV, and tools to clean pipes, such as jetting equipment and back trucks. But SSO still occurred, partially because it was difficult to assess which pipes needed cleaning when. At the same time, he learned that CCTV and cleaning activities were quite expensive and capital-intensive resources, and they were frequently deployed in pipes that turned out to be in good shape, while pipes that needed immediate attention may have inadvertently been skipped due to the sheer number of pipes involved in most of these very complicated systems. Therefore, the SO-RAT was invented to fill a niche for providing rapid assessment of, at the same time, the SO-RAT was developed to provide rapid assessment of overall blockage condition in gravity-fed sewers by using acoustics to yell down one manhole with a transmitter as shown in the attached slide, and with the transmitter in an adjacent manhole. The SO-RAT exploits the fact that sound energy wants to travel down the free space above the flow in a pipe, and the obstacles that can impede the flow of water, such as roots, bad soils and grease, pipe sags, protruding taps, etc., will also impede or dampen sound energy. The SO-RAT receiver knows what the transmitter is yelling, it knows what it hears, as well as knowing the length of the pipe. It uses this information in a sophisticated pattern matching algorithm to give an assessment of blockage condition in the pipe on a scale of 0 to 10, where 0 equals blocked and 10 equals clear, a pipe that's as clear as a clear reference sample. It does this work without any flow contact and in less than 3 minutes. The SO-RAT will work in any type of pipe, such as clay, ductile iron, concrete, etc. Each component is GPS enabled. It is light and portable, weighing less than 30 pounds in total, and each component is powered by a high-performance lithium-ion battery. Having been developed in partnership with a utility, it is rugged, field-tested, and easy to use. And finally, the data can be downloaded either to a PC or to InfoSense's back-end cloud application, where it can be managed or visualized. If you could move to the next slide, please. Next slide, thank you. A number of different approaches or applications have been identified by our customers as noted here. We're rapidly approaching 100 unique municipal installations with over 4 million feet of pipe inspected and customers as far away as Australia. The SO-RAT won the WEF Innovative Technology Award in 2012. It has been the focus of numerous articles, including making the cover of Municipal Sewer and Water magazine in November of 2013. This time I'd like to give you a brief example or a case study of how a municipality has used the SO-RAT in a pre-cleaning application. The city of Augusta, Georgia encountered a situation where they had a 36,000-foot basin that was prioritized for cleaning due to customer complaints of low flow. To clean the basin would have cost approximately $40,000 with an outside contractor. Without the SO-RAT, that's what they would have done. But with the SO-RAT, their crew was able to inspect the entire basin acoustically in approximately 3 to 4 days. What they discovered was there was only about 2,200 feet of pipe that actually needed cleaning. So he was able to deploy their own equipment to take care of the problem, and the savings from this one situation essentially paid for their purchase of the SO-RAT. There are many other stories like this one that we would love to share with you. but in the interest of time, we will pass on that. Next slide, please. This final slide provides a quick recap of some of the key components of what we discussed today. Again, the SLRAD is not meant to replace cleaning or other inspection equipment. It's meant to be another tool in your toolkit that can allow you to assess large sections of your system quickly and at low cost, so as to allow you to better triage and prioritize where you invest your money on cleaning and camera work. This better focus can improve the effectiveness of your cleaning operations dramatically and consequently help economically reduce the occurrence of SSOs. Again, there's more information available on our website. I can provide more information as well. If you have questions or you'd like answered as part of this webinar, feel free to send them on to the moderator. I'll remain on for the Q&A portion for any that may come up. And with that, I would like to thank you for your time on behalf of InfoSense and the Sewer Line Rapid Assessment Tool, and now turn the mic back over to Mr. Rowe.
Okay, thank you, Mr. Churchill. Well, we've received quite a few questions, and let me encourage you to continue to send them in, but we'll start. There's quite a few for each of the presenters. Let me start with Mr. Durr. Does the force main need to be dewatered for this sea snake application?
In this case, because the force main had already failed at one point, it was already dried. So we opted to do the winched pull through, and it did have to be dewatered. The sea snake can also be in a free swimming, where it's inserted hot into the sewer, into the force main or water main, and uses the water pressure to push it along. So it could be either way, depending on what the client really wants to do in terms of disruption.
Okay, related to that, how well does technology such as the sea snake identify deterioration at the pipe joints?
I don't think that, well, the sea snake is purely electromagnetic, so it's not going to tell you anything about the condition of the glands, if that's the question. I have talked to PICA people about adding a an acoustic sensor to see if there's any leaks. They have not done that, but certainly they could if they were asked to.
Okay. Dr. McKim, what is the most commonly used screening tool?
Well, really, the most commonly used screening tool is something like a walkover or historical information that will sort of tell you where the major problems are. That is in-house, and most people have a fairly good idea of where the major problems for their system are, just from operations. So that's the first step. The second one, I think, we're starting to see something along the lines of the guided wave technology is a good screening tool, mainly because it's it's quite inexpensive, and I think it gives you sort of a pretty good information to bang for the buck. So I would have to say the most common screening tool is basically your own records, and after that you can get into some of the other ones like guided wave.
Okay, well, I'll have you, what does did the matrix include both downtime and costs in your cost per length?
Okay, no, it did not. I think you're referring to the pipe out of service. We recognized whether the technology required the pipe to be taken out of service and drained, or whether it could work under full service. That was in the matrix. You could tell that, but we did not include any costs for having the pipe taken out of service, because that's so highly variable. We just actually looked at the price of actually doing the work with the technology, and an individual utility is going to have to price out how much it's going to cost for taking a line out of service.
Okay, Mr. Lambert, I have 3 questions for you. How much did the inspection for the smart ball cost?
The smart ball inspection itself was about $40,000, and then allied costs on our part, including the contractor and operations and construction management, ended up about another $30,000, and it was $80,000 U.S. total.
How did you track the location of the smart ball?
They put sensors along the line at access points. Unfortunately, due to the location, we didn't have a sensor until almost 6,000 feet it's actually a gravity connection to the force main in a manhole about 1,000 feet shy of the treatment plant. They were able to place a sensor, and it tracks as it goes by. So we did have a pretty long wait to see if it had gotten there. As far as how it moves, as long as you have a constant flow, according to the vendor, it moves at about 80% of whatever your given velocity is. Once again, we were able to get that constant velocity, so they were able to simply time it, and it was pretty close to that 80%.
Okay. Mr. Durr, what is the reason for picking a safety factor of 1.2 for replacement instead of 1.5?
We just worked this through with the client. He felt more comfortable with that. 1.2 was really settled on to give him enough time to get serious defects onto his CIP program and give him a couple of years of breathing time before he, ostensibly before it hit 1.0, which is you want to repair it right away.
And the condition assessment codes, is that being done in conjunction with NASCO, and when do you expect a copy to be available?
Well, actually, what I'm showing you here is done internal to Brown and Caldwell, but I will be presenting this to the Pressure Pipe Committee, on which I'm a member with NASCO, on next week. As a matter of fact, we have some technical sessions that we're doing on Friday, and these codes will be presented and discussed at that meeting. And NASCO has just come out with a table of tools, much like the one you saw earlier. And I think they came out with it last week or a month ago. And now we're going to be working with developing these defect codes as well. So we should be seeing something out within the year.
Okay, and does the Sea-Snake tool detect external corrosion as well? In other words, does it take external corrosion into account when calculating the remaining wall loss? And the second that question, can the Sea-Snake be inserted in the force main while it is in service? So there's two questions there.
Good. First question, yes, it can detect wall thickness, whether it's on the external or interior of the pipe. So it calculates the total loss of wall thickness at each point. The second question was, can it be inserted live? Yes. The issue there is that most force mains, both wastewater force mains and water pressure mains, have not been designed or constructed with smart pig or pig launching or receiving assemblies. So typically you either have to break open the pipe and insert the tool, or you have to actually, what we've been doing is persuading our clients that it's really a good long-term maintenance idea to install these cleaning and inspection, insertion and retrieval stacks in your critical assets. If you do have those, then yeah, you can insert them live.
Okay. Mr. Lambert, during your presentation you mentioned the word coupon, or defined it. Can you give a little bit more definition on what, how that was used and what you mean by the coupon?
Oh, the coupon is a portion of the pipe wall that was removed using a hot tapping device. So just as you might hot tap into, put a lateral into a line while it's live, we simply use that equipment. It involves, a tapping saddle and a gate valve and a blind flange. So you get that all set up. They run a hole saw, basically a very steel cutting hole saw down, and pull that piece of metal out, and then you're able to actually look at the piece of metal and see how much remaining wall thickness there is.
A related question, what was the reason for coupon testing in the gas pockets on the beach slide?
Oftentimes, if there are trapped gases, you end up damaging the interior of the pipe, particularly if the sewage is hot, has a lot of hydrogen sulfide. In this case here, most of the sewage is pretty fresh. It's not sitting for long periods of time. So we did not see any corrosion, what we felt would be beyond normal, or in any wall loss. And the wall loss was actually very minimal, which has given us confidence that the pipeline does, in fact, have some good useful life left in it.
Well, have you? Was ice pigging the force main considered, and if so, why was it ruled out?
Ice pigging was considered, but we didn't feel that it would give us any real information. Feedback as far as what we could find out about the force main.
Okay. Dr. McKim, what technologies are appropriate for situations where the original pipe wall thickness may not be known? And that may be broad, but if you can respond, that'd be great.
Very dependent on the pipe material. I think going back to when you don't know what the pipe wall is, historical records are the place to start. You should need to look at the as-builts. If you have a metallic pipe, typically you can get in there and do some fairly good work with ultrasonic testing or coupon testing, as was discussed just earlier. The guided wave technology will give you some indication basically of the wall thickness that's remaining. If you know the Young's modulus and what the theoretical pipe stiffness should be, by taking the guided wave, you can actually back calculate what the wall thickness would be. Actually, you can do that for a monolithic material like steel and or plastic, or you can, the claims are they can do it for a more complicated material like pre-stressed cylinder pipe. You can get into things like the pipe penetrating radar, which is a system that basically holds a ground penetrating radar type device against the inside pipe wall and fires off a signal, radar signal, and you can interpret that fairly accurately to get pipe wall thicknesses. And when we get the ultra-wideband system that was shown very early, that actually is fairly good at getting pipe wall thickness as well. I hope I sort of answered his question.
Related, are there any technologies discussed today suitable for the smaller pipelines, 4 to 10 inches in size?
Guided wave, for sure. I think the sea snake can go down to that sort of size under 10 inches.
Mm-hmm. Yep.
I believe the smart ball can go down, under 10 inches. I'm sure there's a lower limit on there. Off the top of my head, of course, just walking over, having a look at the surface, doing straight current analysis, smoke testing would certainly work with the smaller diameter. So there are a number of technologies that will work in the under 10 inch. You just have to make sure you select the right one.
Okay, and while I've got you, what do you recall the depth of the force main where the C900 was installed in your case study example?
It was varying from on the surface to when it went under the interstate, it was down, I think, about 20, 25 feet. So, like I say, it was all over from surface to about 20 feet.
Okay. Mr. Durr, you found holes in the invert of a partially full steel sewage pipe. Is the invert the typical location for holes in partially full pipe sewage? And the second question, what would the typical location for a full steel pipe be?
Okay, first answer. In actuality, this the 650 feet that had the holes in the invert were actually flowing full, and we think that and we're pretty certain that the holes were caused by external corrosion due to the fact that it was in a saline groundwater in a tidal zone, and it was rising and falling, and so the corrosion was external at the invert of the hole, invert of the pipe. We're flowing full, or flowing partially full, particularly where we have down gradient sections of the pipe near the discharge, where it's constantly flowing partially full. We do see extensive corrosion in the crown of the pipe due to the gases in the headspace.
Okay. Mr. Lambert, a couple questions here. And I have a couple questions for Mr. Churchill. Mr. Lambert, on the North Beach force main inspection, was an assessment value determined? And if so, what were the values and how were the ratings made?
No, the only assessment values that were done were based on wall thickness, remaining wall thickness, and some of the pits that they found in the external portion of the pipe. The smart ball simply tells you whether you have a leak or not, and whether or not, and if you do, where they think the leak is, and if you have trapped gases. There is no overall condition assessment beyond that. And then once again, we had our corrosion consultant do the metallurgical analysis and come up with the general pitting assessment for the 3 coupon locations.
On your siphon inspection, was sonar used because it was a siphon, or was this just selected as the best practice?
I think at the time we were having some capacity restrictions in the siphons, and it was felt that the fact that we could get a profile, a cross-section of the pipe with the sonar, that would be useful to us in locating where the obstructions were. And so it was the fact that we could deploy it and get information while the pipe was full, because for the most part we're not able to completely empty any of our siphons.
Okay. Mr. Churchill, what is the maximum size pipe application for the SL-RAT? And the second part, is there a length limit to its application?
Good questions. Thank you. The pipe diameter for the SL-RAT, the original algorithm was developed to be focused on those 6 to 12-inch diameter lines that make up the majority of most systems. That being said, the physics of the technology work in any diameter of pipe, although as you get into larger diameters, say 24-inch and above, you have to do some more work with what threshold you use to take action based on our 0 to 10 scale. As far as pipe length, how far can it operate? We have inspected pipes up to 850 feet. We don't recommend skipping manholes between tests, so we have rarely seen locations that had manhole or pipe segments that were more than 850 feet in length. Does that answer the question, I hope?
I have some more, but let me ask this one to anyone. This person says they've heard about fiber optic cable can now be put inside mains to determine leaks when they occur. Have any of you used this as a real-time inspection of a main? So
I'm not.
Just open question.
Yeah, this is Kelly Durr. We've used fiber optics for ongoing monitoring of pre-stressed concrete cylinder pipe to listen for wire breaks. I have heard that the same technology can be used to listen for leaks, but it's a pretty expensive. It's a very expensive technology, and I have not heard of actually any client actually doing that yet. But I'd like to hear about it if you know any.
Okay. Any others? All right, Mr. Durr, I have you? No, this is Mr. Lambert, sorry. On your North Beach force main smart ball inspection, did the device deliver areas of pipe wall deficiencies, or was it only looking for leaks? And how did you determine the proper spots to do coupon testing? So there's two questions there. How did you what was the areas, how do you determine the areas for the leaks and determine areas or where to do coupon testing?
The first question, no, it did not give us any information regarding wall thickness. Once again, it is able to tell you whether you have a leak or whether you have trapped gas. And then we used the trapped gas locations. We used some of the identified trapped gas locations along the beach to take the coupons. The thought being, oftentimes when you have trapped gas, you get, depending upon your pipe material, you get pipeline deterioration in the crown from interaction of the trapped gas and the pipe material. You know, specifically interaction between hydrogen sulfide and concrete. So that's just, it was information that we felt would be good to at least narrow down where we took the coupons from.
Related, another question related to your project. Did you consider flooding the force main with clean water instead of pumping down the pipe?
We did use clean water for the test. We basically took hydrant water from the city of Seattle Public Utilities, and flushed it. You know, use that water. The pump station is part of a CSO system, and so it reaches its peak capacity, peak pumping capacity, and therefore peak velocity in the force main on a fairly regular basis, at least once a year typically. We have a CSO control project going on upstream of that now that will be reducing that. But does that answer the question?
Let me clarify. Did you use the portable water to provide adequate? I recall you used it for pushing the smart ball through your force main. But if you wanted to use a CCTV camera, would that have been satisfactory, or have you had any experience with using CCTV in a flooded potable water condition?
First of all, we didn't have access for CCTV. We don't have the ability to take the pumps or take the force main offline. It's a single force main. We do actually have an emergency bypass plan in place in the event that we were to have some sort of a failure. It's a very expensive proposition. It involves trucking and or laying a temporary pipe, and it runs quickly into the millions of dollars just providing that. So doing any sort of, providing any sort of access or taking that offline was not an option for the inspection. So therefore, video inspection would not be a possibility.
Reggie, this is Rob McKim. If I could just add to that, there is a technology that has been in use, I know, in Quebec, Canada, where they used a push camera going in through a fire hydrant. And they've got some fairly good pictures of the potable system through the fire hydrant. So there is some technology developing out there that makes CCTV actually work fairly well under some pressure circumstances.
Okay.
And if I may break in as well, we've used a tool from UK called JD7, LDS 1000. It is a camera, and it can be pushed in or it can be inserted hot, and it's for water mains, but it does give fairly decent CCTV inspections of water mains under full flow conditions.
Yeah, and this is Mark.
Fairly new tool in the U.S. Fairly new.
Yeah, and I, my thought is as the delivery vehicles and delivery techniques come along, that's been a major limitation for a number of our systems. I think as those delivery systems are developed and implemented and deployed, that's going to bring a lot of promise to all of the technologies for use in pressurized systems.
Absolutely.
Mr. Lambert, this is directed to you, but I think any of the presenters can respond if you'd like. Is the smart ball pipe diameter dependent? In other words, do you think you get better results as the ball is closer to the pipe wall?
They size the foam ball relative to the diameter of the pipe that you're in, so I'm not sure if that would make a difference. That would probably be a question for Pure. There are some other, basic conditions that are required for it to work. You have to have relatively high minimum pressures in the line. I think they like 25 psi as a minimum. So if you have a low head system that doesn't build up a lot of pressure, doesn't have a lot of static head on it, it's probably not going to be able to tell you a whole lot. While this is a low head system, the fact that the pipeline drops down quite a ways to the beach gave us the necessary head and pressure to actually, do the leak detection. So, but there's.
If I could add some.
Yeah, it effectively added head. But from one end to the other, the static head from the pump station to the treatment plant isn't real high, but the force main itself is 40 feet below that for most of the 40 to 60 feet below that most of the way along its alignment.
Okay.
If I could just add something to that, I've worked with Pure on a lot of projects, and the smart ball essentially just rolls along the bottom, and so it's and they do change the size of the foam ball according to the size of the pipe, just so it rolls better. They do have a 4-inch for smaller diameter pipe. The typical ball is a 7-inch, and I know they have a 12. But they actually count the rolls as they go through as one of the ways of indexing where the leaks are.
Right. Yeah. That and the timing were the two ways that they can do
that. And the monitors. Yeah.
Yeah.
Mr. Durrett, we have a related question. How does the smart ball determine the location of the leak?
That's a good question. They use the monitoring sites that Mr. Langer was talking about. And he was right. They like to put them every couple thousand feet, and it records. The monitoring sites record when the ball goes by. It has a little beeper that it hears. They also have in their software they count. They say they count the rolls, but basically once they get the data and download it, they're able to index from the time track of when they passed each monitoring point and the roll rate where each leak was as it goes along the route. And I got to admit
Okay.
that they've been pretty accurate.
Okay. Mr. Churchill, we have a couple for you. Will the SL-RAT work on siphons also?
The SL-RAT is focused on gravity-fed sewer, so hopefully that answers the question. It will work in drop manholes. Typically, we recommend putting the transmitter, the part that yells, in the drop section, and the receiver in the upstream manhole. But it will work in them.
Another related question: does it locate the blockage specifically, or it only shows a manhole-to-manhole blockage?
It provides an aggregate assessment of blockage condition in the pipe, so it will not tell you what the blockage is or where it is, but it will give you an assessment that tells you that that is a pipe segment that is worthy of further study with either your jet or vac truck equipment or with your CCTV or other inspection equipment to determine what's going on.
Can it differentiate between sediment buildup and blockages?
It can indirectly detect sediment buildup through the, as the flow in the pipe becomes higher and higher as the sediment builds up in the bottom. You will get a lower acoustic score over time, so it is able to indirectly give you a measure of capacity, but that is somewhat limited. I wouldn't say it can directly give you information on, for example, the percentage sedimentation in a pipe segment. But it can indirectly due to capacity issues. Sorry.
Oh, I'm sorry. Related, how your services, do you rent equipment? Do you operators or purchase it, or how do you deploy your equipment?
All of the above. So we are the manufacturer, so we typically sell the equipment, but we do have a leasing program and a rental program. And if folks are interested, they can go to our website, or they can contact me, and I can put them in touch with our manufacturers reps. We do sell directly through manufacturers reps that have exclusive territories throughout the U.S. and in some parts around the world. So if somebody's interested, they can certainly send me an email at that address, and I will get them more information.
Dr. McKim, what tools are appropriate for measuring invert scour of large diameter surcharged reinforced concrete gravity sewers?
Well, in order to find the amount of scour that you have, I guess if you can empty the pipe, of course the CCTV will give you some indication. If you take a laser profiler or a laser scanner, that will give you exact information on how much out of the round it is. If it's a pipe that's flowing and you can get a sonar system in there, that will also give you a very good indication of how much scour or how much material loss you have in the pipe wall. If you have access to the invert of the pipe, then you can do things like take some ultrasonic testing, which at least in thin wall thicknesses less than an inch seems to be quite accurate. Once you're getting over an inch with ultrasonics, it's a little bit iffier, I think. So that would be the ultrasonics. Also, the guided wave, like I'm saying, it will sort of tell you what the thinnest wall section is between two lines, between 2 points. It may not be able to tell you where it is in the invert or the crown, but it will give you some idea about the minimum thickness. The remote field eddy current materials are the C-snake, not the transformer couple technology. The C-snake technology will also give you 360-degree information about wall thicknesses. So there are a number of technologies out there, yes, that will tell you what the invert wall thickness is or what the scour is.
Another question for you, Dr. McKim. What is the best technology for establishing the horizontal and vertical location of the pressure line?
Wow. So I'm not sure how to answer that. Well, first of all, it should be a good old laser or surveying equipment that you use to install the line. And the as-built should be very accurate, but I think we all know that that's probably a little bit of a problem. There are some technologies out there that tie gyroscopes into the GPS system, so you take a GPS reading at one manhole and put it in, and it measures the up-down turns, and then you tie it into the GPS at the other access point, and it will tell you the information between it. You can also locate it with a GPS, sorry, not a GPS, a GPR, ground penetrating radar. You can hook a GPS in onto the ground penetrating radar and sort of track where the pipe is and get the depth, so that'll give you sort of the location of the pipe. Those are probably the major technologies. I might have missed one or two, but those are probably the big ones that you want to look at if you're trying to establish your line and grade of piping systems.
Okay.
Well, look, can I add one? I'll add one more to that. A couple of our clients actually did not know where their force mains were, so we've actually used Sahara, which has a pinger on it, and it can be tracked from the surface. So we're able to get the XY and a little bit of the Z, but not the Z. So where you don't know where your force main is, the Sahara can actually track it for you.
But actually, if I could just jump on that again, this is Rob McKim again. Yes, I forgot, you can put a sonde, just like a directional drilling sonde, yep, for locating the directional drill head on the Sahara system, and then you get the good walkover, and then you get the depth as well. So that one, I apologize to Sahara, but that's also another fairly good way of understanding where your system is.
Yep.
I'm going to direct this one to all of you. This is interesting. Are these technologies that we've talked about today available in Russia? This person has a project in Russia. So,
there is actually one tool that I've seen that was developed in Russia. It is called the magnetic tomography. It was tested briefly here in the U.S. I have seen, I think the company's name is Tractor or something like that. It is being used successfully in Poland and Russia right now. I just saw a memo on it. I would bet you a bunch of the other technologies are also available in Russia as well.
Hopefully that person is listening and will take note.
Yeah.
Virtual here, I can add that the SLRAT can be shipped anywhere. So if someone would like to buy one, they're available anywhere in the world.
Good point. Ms. Churchill, while I have you on, the maximum percentage of pipe flow depth that the system is usable?
To answer that question, the typical pipe that we see in gravity-fed systems is probably in the 5 to 25% flow rate. So that's typically what we see. At a 100% flow rate, the SLRAT will give you a score of 0 and indicate blockage because the sound energy has no path to pass through the water. So, kind of at 100%, you get a score of 0. Typically, we see pipes in the range of 5 to 25%. And what we see at those higher flow levels, say 75% and above, is typically you will get a reduced score, and frequently that's caused by that smaller head space. Even slight pipe sags or dips can result in a pipe sag situation or a full blockage situation at some portion in the pipe. So hopefully that's helpful for the user. So I guess to recap, the 100% flow is a score of 0. Typically we see 5 to 25%, and when you get above a 75% flow rate, we typically see some degradation in the score.
I'm sorry, I had on mute. Ms. Churchill, can you differentiate between offset joints and sedimentation?
Again, the SLRAP provides an aggregate blockage assessment of an individual pipe segment. So offset joints will have some impact on the score, as could sedimentation or turbulent flow of water, any other things. They're all additive into that one number that we provide. So it won't give you a view as to what particular defect is in that pipe, other than to say there's a capacity issue of some kind in this segment.
Okay, thank you. We had one listener say that Pure Technologies will send services to Russia also. So
I'm sure they will.
Is there, back to you, Ms. Churchill, is there special training or certification required for sewer rat? How do you deploy that?
So the SLRAP was designed with utility operators in mind. So the typical operator can be trained in under half an hour to use the device. There's a little bit more training for the folks in the back office to interpret the data and the results when you download them. But in a half a day's training, you can be fully functional with the SLRAP. And we can offer that, and our manufacturers' reps also offer that training.
This is to any of the speakers. Do you have any case studies where you have ongoing real-time condition assessment of pressure pipelines, and what type of assessment and why? Mr. I believe you referred to one already, but do any of you have any ongoing?
I don't have any, and I'm not aware of any except for some of the fiber optics that are just listening for pings, so no.
Yeah, most of the devices we're using require a little bit of post-processing, so there's usually a little bit of a delay. For instance, the broadband electromagnetic has to go to Australia to get post-processed, but they will give you within 72 hours a preliminary result, but that's not quite real time. So that's probably one of the better ones I know.
Okay. Mr. Durr, was there any size limitations for the sea snake?
Right now, the sea snake goes from 3-inch diameter up to 24-inch. They are in the process of constructing both 30 and 36. So as they get more into this, they're developing more tools. But from 3 to 24, definitely they have available.
Mr. Lampert, on your North Beach project, you thought that there was originally a defect in the force main. How did using Smart Ball and taking coupons alleviate your concern? How did you resolve it?
The initial thought was that we had a blockage in the force main, and that was partially responsible for some of the peak capacity shortfalls that we were experiencing. Unfortunately, the Smart Ball did not tell us whether or not we had a blockage in the force main. We are suspecting now that the loss of peak capacity is due to simple pump wear and tear is the current engineering conclusion on that. As far as defects, we had information from the previous coupon inspection from '89, and we simply revisited very similar, identical inspection at different locations, and we're able to, based on wall deterioration or lack of wall deterioration, that we still felt that there was another 20 to 30 years of useful life in that force main.
Okay. This one can go to any of you. This person has described a fairly lengthy site arrangement, but boil it down here. They've got steel pipe in a plant encased in concrete. They know they have pitting, multiple pipe sizes from 18 to 84 inch. Is there a technology that accommodates a force main with changing pipe diameters that would work in this condition?
Ouch. Yeah, most of the electromagnetic tools are very size limited, so they would not be effective in that, particularly that range of size diameters.
Okay.
Well, I don't know.
The guided wave would work as long as you're going, same pipe size. So if you get access where it changes diameter, you can get some indication. And I would suspect that if you the smart ball and kind of pushed it going from the smaller pipe diameters up to larger pipe diameters so it wouldn't get hung up in the ledge, that might work as well. But it's a very unusual problem, and I sort of hate to give an answer without saying it's going to be very site-specific. But I think there are technologies
may need a little more specific data.
Yeah.
Yeah.
Can any of these technologies we've discussed today be used for inspecting buried aeration piping?
I hate to say it, I'm not exactly sure what buried aeration piping is.
At a sewage treatment plant? I assume.
It does not qualify that.
I guess depending upon the configuration, how many bends there are, how many joints, how many pipe, again, diameter changes in the aeration system. You possibly, if it's a consistent diameter and not a lot of bends, the sea snake could do it. If you're looking for pipe wall defects. If you're looking for leaks, then certainly the Smart Ball or Sahara will work. Imagine if you have leaks in an aeration system, you're going to know about it already.
Let me give you guys another question. What technology is best for getting the condition of very small force mains, say 4-inch diameter from a lift station to a manhole? Is there a preferred technology?
One of the really deep problems with particularly small diameter force mains is that they usually have a lot of twists and turns, which makes it very difficult to put a tool in to inspect them. And 4 inches is a real, if you've got a nice straight run, then Pika does, the sea snake does go down to that size. But at that size, it's going to be very difficult to get around corners, on bends and elbows and T's. We've had several different clients who've had small diameter force mains, really short run, small diameter force mains. And it's been technically difficult to get in, and particularly if they're small diameter and short, it's just cheaper just to replace them rather than inspect them.
Okay.
And of course, you can always use smoke testing and things like soil analysis to find out the potential corrosivity of the soils, and straight current analysis that will sort of give you a global idea of what's happening.
Yep.
Rebecca, we have a multiple list of questions still remaining, but I think our time is about out. Is that correct?
Yes. We can either respond to the questions through like an FAQ, or we can answer them on the Part 2 webcast, which, by the way, is going to be, Part 3, sorry. Oh, it's in September. So we can do that. Is that okay?
That's fine. So do you want to end it? You want me to?
Sure, go ahead.
Okay. Excellent questions. We want to thank everyone today for joining and participating, sending their questions in. Have a great day. Bye-bye.
Yep.
Bye, folks.
Bye-bye.
The organizer has ended the session, and this call will be disconnected. Goodbye.